Morning, everybody. Time to get started. Welcome to PhotoTech lecture number 30. That's some kind of milestone. Today we're really super pleased to have with us Bob Fisher. He's the founder and CEO of Optics One in Westlake Village, California. Bob got his optics training at the University of Rochester and has had all kinds of honors, awards, and positions over the years, including the president of the SPIE, which is the organization formerly known as the Society of Photo-Optical Instrumentation Engineers. I think they gave that up. Now they're just the SPIE. Bob, looking forward to a great talk. Take it away.
Okay, thank you very much for the intro. Appreciate it. I'm going to start out slow, but I'm going to accelerate very rapidly. I have about 2 hours worth of material to present in the next hour. So if you can listen as fast as I talk, we're going to learn terrific. I always like to start out with this one, which is my favorite visual illusion. It's sort of irrelevant relative to the rest of the talk, but it's so neat that I'd like to show you. Basically, if you stare at either one of the crosses, I think you'll see eventually, well, pretty quickly actually, that all the pink ones go away and all you see is a green one. There is no green spot. It doesn't exist. It simply doesn't exist. And if you stare at it long enough, you'll just see the green one go around and the pinks or the purples will completely disappear. The green is after image on your retina is what it is. And purple, like you may remember as a kid getting a picture in a little coloring book of an American flag, and they tell you to stare at it under a bright light, and then 5 minutes later or 2 minutes later look away and you see the inverse colors, the reverse colors. That's effectively what this is. So anyway, that's kind of neat. I just wanted to share it with you. Now, arrow down, I think. Yeah. I just want to cover a little bit of this. This is also a lot of fun. Late invention of telescopes has so exercised most of the geometries that they seem to have left nothing unattempted in optics, no room for further improvement. That was in 1669 from Isaac Newton. He'd turn over in his grave if he saw what we're doing in optics these days. And of course, Bill Gates thought 640K of memory ought to be enough for anybody. So there's kind of neat things there. The world is moving ahead very rapidly. Actually, let me go back to the other one real quick here. Everything that can be invented has been invented. Well, that's a misstatement, as it turns out. If you do enough searching on Google, and that's where I do all my searching, you'll find out that that is a false statement and it's a myth. And the next slide, which I'm not going to stop on, tells the whole story. Okay, today's presentation, imaging optics for the next decade. We're going to see in our lens systems and other imaging systems, we're going to see more increased use of non-spherical or aspheric surfaces, and I'll show you why in a little while. Any of you who are into digital photography, this should feel you'll feel right at home with all this. Compression molded glass lenses and injection molded plastic lenses, often with aspheric surfaces, again, are going to be very prevalent. Diffractive optics, where we use basically the physics of a diffraction grating to bend light, can have some remarkable advantages over conventional surfaces. Improved image quality. As sensors become smaller, pixels become smaller, the task focuses right on the optics as one of the weak links in the chain unless we come up with better designs. More compact zoom lenses. You'd love to put it in your shirt pocket and have a 12x or a 15x zoom. Well, you don't have that yet, and I'm not sure you ever will quite to that extent, but they will get smaller, they'll get lighter in weight, and they'll get cheaper as well. More efficient stray light control. That's something that comes with the territory. Any lens system, if you aim it close to the sun, even if it's outside the field of view, you'll get some flare and glare and other problems. More robust lens assemblies. Now a lot of cameras are underwater, for example, and things like that, and lower cost optics. A few words about basic optics. Let me push this twice. I didn't do that in the first place. Okay. The goal of virtually any image forming system is to be of sufficient quality to resolve a minimum sized object, namely each one of these, what I like to call resolution elements. You could call them pixels if you'd like. And the image blur must be matched or should be matched to your smallest detector size, namely that of a pixel. That's a good rule of thumb. It's a handy dandy rule of thumb. In addition, the clear aperture and the transmittance has to be sufficient for the desired sensitivity. Your imagery is no good if the sensor can't pick it up and have sufficient signal to noise to be able to give you an image to look at. So that's the purpose of the performance of our optics. the design form must be capable of meeting that performance. You're not going to be able to use a magnifying glass as a front objective lens for a long telephoto or for an astronomical application or anything like that. A magnifying glass is one lens element, and the image will be exceedingly blurry and just it won't perform well. Special requirements we may have in the infrared and other wavelengths must be met, and minimize size, cost, weight, environmental effects, and there's a whole list that probably would add on to that as well. If I take a P2 cruiser, make it monochrome, and then split it up into 5x11 and these various other numbers, clearly you can see the car here, here, and you can barely see it here, but I speculate, and some experts in image processing have concurred with me, that motion is a cue that's extremely important, and you probably would be able to tell what it is if you saw the car driving across in the 8x16. I just added this slide to my lecture recently. If you have a tank or a cannon or a person, these are the number of bars or resolution elements that you need in order to resolve, to detect, orient, recognize, and ultimately identification. You're going to need 6 bars across the object in most cases. So that's what we're dealing with when we're talking about pixels. Now, how does a lens work? I meant to bring this along, but in the hustle and bustle last night, I didn't pack it. But I call this a wire lens. I have an optical axis here where there's a piece of piano wire. It does kind of a loop here, so it pivots about this point and it continues on. Up at the top, I have another piece of piano wire. It comes to here, it loops around. There's a screw going into the wood, and it comes down this way to here. And then this one, and this one, and this one. So I have parallel, what I'll call wire rays, or whatever you want to call it. And each one, as it gets progressively further from the optical axis, bends the light or the rays more severely so that they ultimately all go through the focus at the letter F. And that's how a lens works. If I take this bundle of rays here, or wires, and I send them in at an angle going uphill to the right, indeed the image is out here above the optical axis, but it still forms an image. If I gather the wires here, I come out collimated, which would be meaning it focuses effectively at infinity. If I put my wires together at 2 times the focal length from the lens, this being the lens position, it re-images to 2F on the other side. And then this one simply shows if I have converging light, it focuses closer than the focal length. So you can look at this and you don't have to know anything about optics or physics. This is how a lens works, and this is the function of a lens. I'm going to skip over this pretty quickly because we don't, just for the sake of time, but basically these are the specifications that an optical design person would work to. This has most of the specs in it that are important. Perhaps the most important tied together, the focal length, which is this distance here. And if I put a single lens here and I eliminated these and the light came in from infinity and came to a focus right here, that would be the focal length. It's taking this black ray and extending it forward as if it was not bent by the lenses, and it meets the entering ray at the very edge of the aperture here. That's the focal length. Clear aperture diameter, let's call it self-explanatory. And the F number is focal length divided by clear aperture. Now, years ago, maybe 10 or 15 years before digital cameras came along, anybody who was into photography knew what an F number was. Now, I hasten to say nobody does. So we have to keep the spirit alive a little bit, and we actually have to work with that in doing our design work. The only other point I want to make here is that the specification for field of view has to be the full field of view. It cannot be just vertical or horizontal, because in this particular case, the diagonal is significantly larger than the horizontal or vertical. And I have seen almost $1 million programs fail in aerospace companies because they designed their optics to go from here to here and ignored anything out in the corners. So that's called a word to the wise. Aberrations, diffraction, image quality, and optical path difference, some very key metrics that we work with. First of all, geometrical aberrations. A lens, if it could form a perfect point here at the image, then you would get what's called an airy disk, which is like a little Gaussian with a ring pattern around it. However, these are geometrical aberrations predictable to many decimal places. This is called spherical aberration. The edge ray focuses or crosses the axis here, and as we proceed towards the optical axis, the crossing point extends outward to the right, and this is what's called paraxial focus. That's where rays infinitely close to the optical axis will focus. If I had a perfect image here, as I said, I'd get a diffraction blur. If I had a very blurry image here, I would not see the effect of diffraction at all. All I'd see is the effect of the rays not coming to focus. So it's one or the other, or some combination of the two. Now, when I first started teaching my course, I wanted to explain diffraction without any Bessel functions or integral signs or anything like that, which to me is sometimes intimidating. So think of it this way. We have a swimming pool at 3 o'clock in the morning, and the water is like a sheet of glass or ice. It's perfectly flat and straight. We throw a rock into one end of the pool, and the wavefronts emanate out in a concentric fashion from where the rock entered the pool. Well, there's an exact correlation between electromagnetic theory in terms of diffraction and also the way water waves behave using the exact same derivations and Bessel functions. So if at the other end of the pool I have a very long radius to where the rock went into the pool way out here somewhere, so they're almost straight. So let's consider them straight. I then put like a part of a 4x8 piece of plywood, immerse it partway into the water. These waves continue to propagate. There's nothing evident here, and we get little curls occurring here. There's no such thing as a step function in the water. So that is diffraction of water waves, and if we substituted light for that, we would get a gradient with little intensity variations up here. And if we get diffraction around a lens that goes in and out of the screen, if you will, we get our symmetrical airy disk, which you can see is sort of an extrapolation, if you want to think of it that way, of this pattern here from just an edge. So that's where diffraction comes from. The airy disk, which is this Gaussian-like image, the physical diameter is 2.44 times the wavelength times the F number. And let me just say, as a quick rule of thumb, in the visible, that diameter is the F number in microns. So if I had a sophisticated or a simple camera lens, and it was F1, I would have a 1 micron diffraction blur. If it was F10, it would be 10. F100, it would be F100. I mean, it would be 100 microns. The angular diameter is 2.44 times the wavelength divided by the clear aperture. So if I have, in this case, 3 different F number lenses actually located here, the first one image is here, the second one and the third, the image gets progressively larger based on this equation here. And I will not bore you with too many equations today, I promise you. If I have 3 lenses here of diameter D, 2D, and 3D, and they have the same F number, the airy disk diameter is identical, and it's clear that this will subtend a hypothetical angle alpha. This will be half alpha because it's a longer distance here, and this will be alpha over 3. So it's the same size blur, but a longer distance means that the angle it subtends is smaller. So if you're doing anything relative to high-resolution optics, this helps quite a lot. I think I'm going to pass by this one. How am I doing in time? Okay. I don't want to get too crunched at the end. Generally, in optical fabrication, we use this kind of process where we have what's called a block. We rotate it about this vertical axis here, and these are lens elements whose upper or outer radius is effectively, the goal is to make it spherical. And then on top, we have a tool of the particular radius we're interested in, and this part here rotates that whole tool assembly back and forth according to where those arrows show. Now, as this rotates about the vertical axis and this swings back and forth, we get a near random situation. It's not completely random. There's overhang on this side and then this side, and the center elements don't overhang at all. But it's so close to random that if the person in the shop varies the length of this and the speeds and so forth, they can create essentially a spherical surface very quickly. One of the beauties of a spherical surface is that the rate of change of slope everywhere on a sphere is absolutely identical. So if I took a tangent to a sphere and moved it somewhere else and then moved it another similar increment, the angle of the tangent is going to be identical at each position. This is one of my favorite slides of the past, actually many years. Where do aberrations come from anyway? You don't have to know anything about optics and you're going to believe what I say because it's very simple once you look at it this way. Aberrations are the failure of the rays from a common object point to come to a single or common image point. And you saw how we had the blur before. Real rays obey Snell's law. We all learned Snell's law in high school. At least I remember learning it in high school. N sine theta equals n prime sine theta prime. The prime got stuck down here somewhere. Paraxial rays, which is the small angle approximation, the sines and tangents in the equations become the angle in radians. So n theta equals n prime theta prime. And that's the small angle approximation. So and paraxial optics has 0 aberrations. It's absolutely perfect in the geometrical sense. So if I take a ray coming in here, the paraxial ray goes down according to the blue arrow, and the real ray refracts more severely because it's obeying Snell's law, which is a nonlinear equation. This is a linear equation. And the difference between the two is what the aberration in effect really is. So if I had theta as 1 degree, the real is 0.5001, paraxial, meaning the small angle approximation, is 1/2. The difference is almost 0. It's a little tiny number, 3 zeros, 1. If I go right to 40 degrees, for example, I find that the real ray descending angle is 34.6 degrees. The paraxial is 20 degrees. So the paraxial is here and the real one is here, and the difference is about 15 degrees. That's pretty much close to what I show here. And that's where aberrations come from. That's the root of any aberration for any lens system you'll ever work with. This shows the real rays in green after they enter the lens here. It's basically a flat surface and then a curved surface. And this is the paraxial lens where the red rays are, and the red rays come to perfect focus. The real ones obey Snell's law, and they come down an image here from the very edge of the aperture. And this angle from the green up to the red is also about 15 degrees, give or take a degree or two. Now here's another lens with spherical aberration. And these are bad things. These are things that we have to get rid of. If we take a single element and curve it around this way, the aberration is so large it's bigger than the lens itself. I mean, that imagery would be absolutely, positively awful. If we take an equal radius on both sides, equal and opposite, we still have a residual, and then bending it this way gives us something not quite as bad as this. If I bend for minimum spherical aberration of the lens, I can get down to a fairly small blur, but it's still nowhere near as good as you're going to need for many applications. One way that we can overcome the problem is to eliminate the very steep angles of incidence at surfaces like here or up here. And we can do that by splitting the lens into 2, 3, 4, and multiple components. And you'll see evidence of that in just a few minutes. There's a term which I want to develop called optical path difference. And basically what I'm referring to here is that if we think of this rock into the swimming pool in reverse, we have the wave fronts in the water coming to a focus point where the rock entered the pool. And that's exactly the same as light coming down with to a perfect focus somewhere over here. That would be the wavefront would be the blue spherical reference wavefront. If the lens has aberrations, then you will see the wavefront will be perturbed. It could be this red curve. It could be something very much different than that. But the difference between the two is called optical path difference. If that number, that OPD, optical path difference, is less than or equal to 1/4 of the wavelength that you're working with, namely a 1/2 micron in the visible, then your system will be almost diffraction limited and you'll see that airy disk pattern. The wavelength in the visible is 25 millionths of an inch, so we're talking about this number being 6 millionths of an inch or less. So whenever I talk to mechanical designers, they go into la-la land when I say 6 millionths of an inch. They have no comprehension of what I'm talking about. And I'm sort of joking here, of course, but it is a very, very, very small number. And if that OPD is less than or equal to 1/4 of the wavelength of light, then you will get an almost perfect image. I'm getting a little bit deeper than perhaps I should here. This is more or less the same thing I showed before, the OPD, what's called peak to valley. That means the maximum to the minimum, the leading to the trailing extent. What if I have a wavefront that is perfect from here to here, and then it just has a very sharp hook in it? Well, that's going to have a peak to valley that's the same as this because it's leading to trailing, but most of the wavefront is perfect. So for that kind of application or result, we use what's called RMS, which is this equation here, which does more averaging over the surface. So if I were to make a telescope mirror as big as this room here, and I had a little dimple or a little raised area the size of a pencil eraser, that was one wave, one visible wave, it would not meet this criteria of being quarter wave in terms of quality, but the area is so small that it would have a negligible effect, and this equation is a better one to work with. So I hope it's clear. This shows what happens if we have 0 waves, that is a perfect image, a quarter wave, a half wave, and 1 wave. And you can see that at a quarter wave, which is this so-called Rayleigh criteria, that's the OPD being a quarter wave, we have a pattern that is a little bit degraded from this one, but we still see the first bright ring is continuous. As soon as we get down here and here, we lose our first ring almost completely. Lens configurations. It turns out that the proper configuration is one of the keys to the art and science of lens design, and I do call it an art and a science. It provides the base, the starting point for your design effort, and the programs, the software that we all have access to. I put quotes around the word automatic, but they're rarely capable of changing configurations. If you go in with a certain configuration, and I'll show you a grouping of them in just a minute, the program usually reaches an optimum for that same starting configuration, but it changes the radii and the shapes of the lenses and so forth. That's called the local minimum in the error function. The configuration can be driven by any one of the specs that I showed before, or some of these as well. A simple lens, magnifying glass quality, small field of view, light bucket. However, they may not be that bad, and I'll get back to that point a little bit later. A landscape lens is the old Eastman Kodak cameras from the 20s and the 30s, where they just simply have a curled lens around what's called the aperture stop, where all the rays pivot about here. Up to 30 degrees field of view, but you have color aberrations and the quality is not that good. An achromatic doublet's the first lens where we can now bring the color under control, and we can bring the red, blue, and green to a common focus, or almost a common focus. So that's called an achromatic doublet. A Cook triplet is a kind of a milestone in a way, because this is the first time we have enough individual things to vary so that we can bring the performance to a rational state of perfection. We have 6 radii, 1, 2, 3, 4, 5, 6, and the 2 airspaces. The thickness of the elements are not that helpful. Sometimes they are, but in general they're not. And we can control spherical aberration, coma, astigmatism, axial color, lateral color, distortion, and I always forget which the last one is. But one other, the focal length, of course. A Zeiss Tessar, for example, is an extrapolation of a Cook triplet where the last element is using 2 different materials to help with the color correction. So you can see sort of a logical trend as you go down these. A double Gauss lens is what you would have in a low F number film camera or digital camera with a fairly sizable sensor. Low F number, perhaps even f1.4 or even f1 in some cases. I won't go through each one of these, a Petsfall lens, a telephoto. A wide angle I'll show you on the next slide exactly how that works, and an eyepiece, which would be a viewer for a display or other eyepiece application like a telescope. A wide angle lens, this particular lens covers plus or minus 90 degrees, so it's 180 degrees field of view. Now if you think of it, light coming in this way, it has to be horsed around rather significantly, and eventually it comes out of this front group of 3 elements with an angle of about that angle relative to the optical axis, and then I take this group to basically re-image the position here where these rays appear to come from, and it re-images onto the sensor or the final image plane. So this effort here, going from A prime and B prime to A and B, is taking us from some position out here to the final image. We take that as a unit, we marry it to these 3 elements, and we have a 180 degrees field of view lens. Now, I don't expect that you'll be able to go back to your office and do all that in the next 20 minutes. It takes a little bit of expertise to get there. But this shows that it is rational. It's not voodoo. It's not rocket science. It's challenging, however, I will say that. How can we continue to improve aberrations? As I said before, as pixels get smaller and sensors get smaller, we're going to have increased needs on our optics. Well, one thing I haven't talked about yet is refractive index. That's basically how much the light slows down as it goes into the denser medium, namely the glass. And from Snell's law, that also defines how the light bends or refracts at each one of the surfaces. And let it suffice to say that if I take 3 elements with an ordinary glass type, and I'm not going to bore you with any greater details than this, of an index of 1.5, that means that that's the ratio that the light slows down in the denser material. And then I go to higher and higher refractive index, denser materials, denser glass, heavier glass. The optical path difference goes from about 2 waves to about maybe 1.5 waves to 1/4 wave. And if I go even further and make a denser glass than that, I ultimately am plotting on a scale of 2/1000ths of a wave, so this is far less than 1/1000th. And that's one method of making aberrations go away. Another method is the configuration. It turns out that this I call the classical configuration, but if we curve this lens element in the front in the opposite direction, so it's curved this way, this was 2 waves here, this is 7/1000ths of a wave. And that's because we're getting balancing of the 3 elements. So there's a lot of tricks to the trade in this business. This I only made up a few days ago, actually. What this shows is that if I go from, actually I should have started at index 1.5 way up here. I then come down basically with the other glasses, I come down about 5 orders of magnitude of the spherical aberration. And that's a lot. 5 orders of magnitude just by using a slightly different glass is rather remarkable. Current state of the art in digital cell phone cameras. I have an iPhone, which I dearly love. I don't really know what's in it, but I do know a lot of things about it that's on, I want to say, searchable on Google is how I got there, obviously. The typical iPhone specs are a 1/4-inch CCD measuring this dimensions here. The pixel size, the individual pixels, are about 2.2 microns on a side. That's getting pretty small. It is said in the literature that in about 2 or 3 years, we may be down at 1.2 microns pixel size. And that would be compatible, or that would be indicative of a 6 megapixel sensor. Right now, the current iPhone is about 2 megapixels, and it's not bad. This is a lens which, although it is bigger than we'd like in terms of scale, the focal length is only this distance here, so in theory, I could put 1 element here, but I would have lots of the aberrations that I talked about. In any case, this lens gives performance that is actually quite good. I'll show you on the next slide how the image blur compares to a pixel. This is an airy disk, and that's a pretty good rendition of it. These are the various specifications. It's 1.92, which is close to 2 megapixels. So that would be compatible with the iPhone, except that it's too big. I think I'm going to skip the spreadsheet. This is a similar design, I believe. I'm not going to compare the two. The pixel size is, again, 2.2 microns. Now here, this total length here is 17 millimeters. This one is 9 millimeters. This one is 4.6 millimeters. This is what we will ultimately be driving towards for the super, super compactness. And the performance is not quite as good as this one, but there's definite hope and promise that it can be brought to that level. So that's kind of at least close to the state of the art that you would see in these cameras. The squares are 2.2 by 2.2 microns. The airy disk is 2.4 microns in diameter. So this is taking a whole grid of rays and sending them into the lens at different positions from the center of the field of view to the outer periphery of the diagonal. And most of the energy does fall within a pixel. I'm not going to spend too much time on this. This is probably the most common metric in terms of optical performance in digital cameras. Let me see what time. Okay, I'm doing fine. And it's called the MTF, or modulation transfer function. And basically that is contrast, I'm going to call it here. Just think of the word contrast versus line pairs per millimeter. And the higher the curve, the higher the contrast. And basically, if you think of, let's say I would take a whiteboard up here and I would take black tape 1 inch wide, or let's say 2 inches wide, and I would put a piece of tape and then a space 2 inches and then another piece of tape. Everybody in the room would be able to resolve those big pieces of tape that are adjacent to no tape and the white, so it's black and white. And the contrast to your eyes is going to be very high. Now, let's see who's got a good shirt for me to point out. I don't see any good shirts, so let me just say, instead of the 2 inch wide tape, we take tape a 1/4 of an inch wide, and then a space a 1/4 of an inch, and then a tape and a space. Eventually, it's going to get so small that the aberrations are going to begin to predominate, and you'll begin to see blurriness even from your eyes, as a matter of fact. And That is the contrast as the number of pieces of tape or the number of line pairs per millimeter increases. So that's what that curve means. There's encircled energy, which tells how much energy falls within a pixel. I'm not going to stay here very long because I think the graphic is better to see. Here's a very important point. I'm never sure where to put this slide, but a word to the wise. This is another handy-dandy tip to keep in your mind. If you have a lens here, let's say it could be a camera lens, it could be anything, but let's say you bought it as a unit to look at infinity like a camera lenses typically are used to do. And now you decide, well, what I really want to do next Saturday morning is I want to take my postage stamp collection and I want to take close-up pictures of my postage stamps. So I put the stamp here, I move the image outward, which is from first-order optics what you need to do, and then I start taking pictures. Well, from infinity, a pinpoint at infinity, a point source like a star, would be plotted, the blur would be plotted on a 25-micron scale of the image plane or the sensor. If I keep the lens exactly the same but move the object to here, the scale increases here to 500 microns. Very, very significant difference. So if your lens was not designed for close-up photography, don't use it for that. They make what they call macro lenses, which are finite conjugate, which means close object, close image. But you could get into a heap of trouble with that one. Now, these are, just to give you a flavor for the most sophisticated form of optical systems that you'll probably ever come across, it's lenses for microlithography, for doing the step and repeat imaging, and then there's etching that takes place on the wafer and so forth and so on. And this was from a paper given some years ago. I'm not going to go into the details of it, but this is about 17 lens elements. And you can see that each one bends the light a little bit more, so the angles of incidence are being minimized, and that's how the aberrations are gotten rid of. Now, I always like to show with this slide, this element here looks like it can go away because it's not really doing much of anything. The light comes in, keeps going pretty straight, and comes out pretty well parallel to the way it went in. And if Dr. Glotzel were here with us this morning and I would ask him why that lens is there, he'd refuse to answer the question. That's because he doesn't speak any English. Actually, he passed away 3 years ago, so that's another probably more pertinent reason. But all jokes aside, this lens probably could be gotten rid of. So if you ever deal in lens systems, the computer drove it in this direction and the mechanical design was probably finished, so they said, hey, leave the lens in there. This is a 30-element lens that's from a US patent. There's the patent number. You can see the very small incremental redirection or bending, if you will, at each one of the surfaces, and therefore the angles of incidence are small and the aberrations are very, very, very low. This lens is probably capable of getting a 5-to-1 reduction, probably giving you submicron, maybe half micron, third of a micron spot diameter for an excimer laser in the deep UV at the final image. This particular one is the one from the previous slide, just to show that that was actually a hardware design. One of the aberrations that we sometimes get into is distortion. And the thing to be careful of here is distortion does not change your image quality, your resolution. The MTF will be virtually identical. It's a mismapping from your object grid, which might be a square grid like this, to the image. In this case, it's called pincushion distortion. This is called barrel. And you can predict it to many decimal places. It's a mapping error. Now, the eye doesn't like to see imagery that looks like this, that has that. And I think the next one shows different amounts of distortion. About 2% is what we usually say that is the maximum tolerable for a visual system if it's designed such that the user will barely notice it. And of course, we can take a single element with polychromatic light, and we'll find that the blue light refracts more severely than the green or the red, and we get a spreading of color here, and that's what we use the achromatic doublet for, to bring the red and the blue to a common focus with the green defocused over to there. Color fringing is prevalent in binoculars and a lot of other visual systems. Don't go home and throw your binoculars away. You've never noticed it yet, and today you're going to look through it when you get home and you're going to say, oh, the imagery is awful. But just remember, you never noticed it before, so don't throw your binoculars away. And actually, in all seriousness, this is towards the outer periphery of the field of view. generally, you take the quarterback at the football game and you put him at the center of the field of view, so you really don't notice the color fringing at all in many cases. This is an important one. It's a little tough to explain, but let me give it a quick go here. Let me take a look at my watch first. Okay. If I take 3 different image positions here, and the red, blue, and green have nothing to do with wavelength, they're just to differentiate the different positions. And I put a compass point at the green crossing the axis right there, and I draw a circle here, and then I move to the blue, and I draw a circle here, and the red, which is despaced to the right, of course, I draw a shallower radius out here. If I do that, and this distance between each pair is 1/4 wavelength, that says that the imagery will be diffraction limited, or nearly so. So this is taking this quarter wave criteria and extending it to what's called depth of focus. So if I move the image in or out from the green to the blue to the red positions, the light comes down at exactly the same way it did beforehand, but it will be almost indistinguishable from diffraction limited because it's less than 1/4 wave. The lens design challenge is to leave these local minima, if this is what's called the error function or the merit function. This is the goodness, if you will, of performance. The lower the curve, the better the performance. The higher, the worse, the more image blur there is. And a computer program will take you here, and then you're varying certain radii and air spaces and thicknesses, perhaps. And then the computer will bottom out here, and it'll say, okay, say figuratively, okay, what do you want me to do next? I've done everything I can for you. Well, what you'd like to do is to jump over this hump here and come out to a better solution here, and maybe even a global minimum, or where the performance is the best possible. Well, there's one very important point that's missing here. What I've said so far has nothing to do with manufacturability. So you might have a computer program that'll bring this to identically 0, but it may be very sensitive to manufacturing tolerances, which means, so what? What have I bought? And that's a very, very important ingredient that the designer has to factor into the design as the lens is being designed, not after the fact. I like this one. Why is lens design fun? This is sort of my little commercial here. We watch the merit function, which is the measure of performance, and that's equivalent to the line of wheels here. And if you think of watching the merit function proceed just like playing a slot machine, you yourself will experience an indescribable adrenaline rush and satisfaction that lens designers have experienced for many years. And there is some truth in that. It's because you don't know where the next iteration is going to take you. If I had more time, I'd expand on that a little bit more. I was going to skip that one. This shows a double Gauss lens for a 35 millimeter application. It was in 1980, so digital wasn't quite here yet. F2, 30 degrees full field of view. And one of the problems that was sent around the community of designers was to change it to F5 with a bigger field of view. And what the committee did that took this on was to put together a report or a paper that was published in the proceedings. And here are 3 designs that evolved. Let me look at the middle one first. This is contrast versus line pairs per millimeter. I call this a happy lens. What's a happy lens? A happy lens is where the bending at the surfaces is fairly mundane. Angles of incidence are not extreme. Aberrations are relatively under control. Packaging is good. It fits in your shirt pocket, etc. This lens, meeting the same specs, has worse contrast. Look at the angle of incidence here, almost 90 degrees. Awful, absolutely unproducible, positively unproducible. Not to mention the fact that it's bigger in size and it has other problems. This one is almost a combination, sort of a hybrid between these two, and probably has the best performance as well. So if someone comes up and says, gee, I got a beautiful design for you, and they show you this drawing, now you'll know enough to say, no, that won't hack it. The US patent system, when it comes to lenses, is in a state of confusion, is what I would call it. I'm not sure what to call it. I've taught my course twice at the US Patent Office, and I had a wonderful audience to speak to at that point. But basically, these are 9 Cook triplet patents. Each one is different, and they're all US patents. And I hasten to say the difference between most of them is negligible. 1924, 1965. This is 1992 or 3. It's right up here somewhere. And I'm not going to read through this, but you'll find a lot of patents if you do any searching on lens systems. They give you all kinds of inequalities that, for me, a lot of it's gobbledygook. They're just trying to, what do they call it? Barrier to entry is what the term that's used. 0.1 times the focal length is less than the refractive index, plus the focal length of the second element, which is less than 2 times the focal length, or something like that. Mumbo jumbo. Glass selection. Glass is generally characterized, and I'm going to try to speed up a little bit because I want to finish on time. Let me just take a look. Okay. Refractive index this way, what's called Abbe number or dispersion this way. It's a reciprocal type of relationship, so the smaller the number, the bigger the dispersion, like a prism would spread light from across the spectrum. Alistair, one of my colleagues, Alistair, wave at everybody, and I did some work for one of the largest glass manufacturers to help them learn how to use different glasses for better performance. And we basically divided it into 6 different categories. We call them balloons. And one would be the positive element in a multi-element lens, low average dispersion, very common glass. And then as we get to higher and higher indices, the aberrations decrease. And that says it, lower monochromatic aberration. Now, very much of an aside, I just saw last week in one of the journals that Casio has introduced a lens using a clear optical ceramic, which they claim has a very high index, which it probably does. We've had zinc sulfide that's clear for years and years, and it's probably as good or better than what they're using. So it might be just PR until I see more about the material. And then some of the plastics are here: COC, acrylic, polystyrene, and polycarbonate. I'm not going to bore you, I don't think, with this one, although this is a very important one, but let me keep going for the sake of time. Digital cameras, a case study. This is, to me, very interesting. Nyquist frequency is the maximum spatial frequency that you can resolve without aliasing. And it's basically the frequency of the, I don't know, the rows or columns of this pixelated sensor. So this is a pattern which matches exactly to the Nyquist frequency: bright, dark, bright, dark, bright, dark, in synchronism with the actual geometry. This is undersampled, which means I have more spatial frequency within a pixel, so I can't really resolve these things. And this is oversampled, which is a much bigger pattern. Now here's the crux of it all. This is actually it's a true story. All my stories are true. Assume we require a new lens for a digital camera with a 3rd-inch CCD. Now this is actually stated after my very first digital camera from Sony. This is the size of the sensor, 6 millimeters diagonal. The focal length is comparable to a 35 millimeter camera with a 35 millimeter focal length. And the focal length here should be 4.8 millimeters to meet that requirement. F2 for adequate sensitivity at low light levels. I simply picked that out of the air. If I had 640 by 480 pixels, it'd be 7.5 micron pixel pitch. That's between adjacent pixels. And that's a Nyquist frequency of 66.6. I should have changed that to symbol. Line pairs per millimeter. The diffraction blur is 2.8 microns, but the pixel pitch is 7.5. So we have a mismatch here. The Rayleigh criteria says we have plus or minus 8.6 microns depth of focus. Okay, now here's where the magic begins. This is a single element with a focal length of about 4.8 millimeters. Very, very small. I call it an aspirin tablet lens. Now, when I first bought the camera, I looked in the manual, and the manual said everything from 21 inches to infinity will be in focus. I said, wait a minute, that can't possibly be. With my ordinary lenses, I focus on the tip of somebody's nose, and their earlobe is fuzzy. Focus on their earlobe, and their nose is fuzzy. So what's going on here? What do they know that I don't know? Well, there's a relationship for calculating how much the image moves or should be refocused as a function of object distance, which is where these red dashed rays would be emanating from a position way out here somewhere. So if I look at focusing the sensor right at infinity, that is to say the black rays here focus right on the sensor, and then I move the object to 3 meters, 2 meters, 1.5 meters, the image distance will defocus by this much, and if I leave the sensor where it is, it will create a disk of light, 0, because that's where I start from infinity, 3.8 and so forth down to 11.54 at 1 meter, and at 21 inches, which is approximately this distance here, 23 microns. Well, 23 microns is much bigger than a pixel, so that's not acceptable in my book. So what I did is I said to myself, I think I figured it out, and it worked out perfectly. I nominally focused the lens at 1 meter. So 1 meter would be where the black rays come to focus. Then I went negative. I got to make sure I say this right. Okay, that's at 1 meter. I then go to infinity and a half meter at these 2 points, and I get 23 microns focus shift. That creates a disk here, 11.5 microns at 21 inches and infinity. Now, 21 microns, I'm sorry, 11.5 micron blur diameter, that's what I meant to say, is about 1.5 pixels. That says, in my book, the Sony camera with a VGA sensor and a pixel pitch of 7.5 microns will focus adequately from 21 inches to infinity, which was what I was hoping I'd prove. But that's why it's true, and it's true because as the focal length gets shorter and shorter and shorter, the amount of refocusing as a function of object distance decreases with the square of the distance, or the focal length. It's very significant. Now, if we follow some of the trail of digital cameras, we had 1/4-inch chips, 1/2-inch chips. I'm not sure which designation these are, but they're progressively larger, and you can see the size on some of them. If I took this as being the benchmark, that is my Sony camera lens, the total length is about 14 millimeters, focal length is 6.4. I thought the other was 4.8, but anyway, it's pretty close to that. If then I scaled up in order to go to the blue sensor instead of the red one, this was for the red, this is the blue, I have to scale the lens up 3.5 times. So before I had a lens that was a tiny little thing sticking out the front of the camera. Now I've got a bigger lens because my sensor is bigger. And if my sensor goes up to this, which is it's about 24 by 36 millimeters, which is 35 millimeter film dimensions, then I have a lens where I have to scale it up 5.5 times. The focal length is 35 millimeters. The whole lens is a big hunker, just like we were used to in the latter days of film photography. So you will have to be really cautious how you design the lenses, make them suitably compact, and so forth. The marketplace has increased 5 times since the year 2000 for digital cameras. Sales in 2004 were 53 million cameras with revenues of $24 billion. In 2008, 100 million cameras will be made, and each one of them will probably have 1, 2, or 3 aspheric surfaces. So I'm going to skip a few of these things. Testing, I just felt I should talk about it, and I have already, so I'm going to skip that. This shows that for a perfect system and a 1/4 wave, there's criteria for diffraction limited performance, and then a 1/2 and 1 wave. This is lower in intensity than this, but the character of the image of a point source is very much the same, and here we begin to lose image quality rather rapidly. Now, I'm not going to read all of this, but I'll read just 1 or 2 points here. In 2003, this was predicted. I should probably correlate that and see what it really was, but about 250 million glass aspheres were manufactured, and this is largely in Japan for the Japanese camera industry. Compression molding can go from 1 millimeter diameter to 80 millimeters with typical diameters of about 1 inch or a little bit less. The residual surfaces are good enough in most cases so that you will maintain your diffraction limited performance. Now, this is the aberration, the spherical aberration. Let me check my, I'm getting real close here. If I were to make this curve flatter at the edge, it would push this ray to meet the paraxial ray, and all the rays would meet there, and that's exactly what I'm going to show you in the next slide. This is lots of spherical aberration. The shallower curve, which is what's over here also, is such that all the light focuses right to a point here. So that's by taking this steep spherical surface and making it gradually flatter and flatter, and it's a hyperbolic shape. This is for correcting what's called astigmatism by putting a little rolled up edge towards the outer periphery of the lens, making it non-spherical, gets rid of the astigmatism. If I take a 3-element Cook triplet and I make all spherical, no contrast whatsoever down in this region here, 1 aspheric, 2 aspherics, 3 aspherics, and all aspheric, you can see the progression of the performance getting better and better. This is the Polaroid SX70 camera. It's a beautiful device. I just don't have time to go into it here. If anyone's interested later, I can discuss it with you. That's a reflective system. Injection molded lenses. We had a project many years ago where we had two acrylic elements, and this shows the progression of this is called an interferogram, and this shows the departure from perfect shape, more or less like a topographical map. And this enables us to determine whether the performance is adequate. And I'm just going to go through these pretty quickly. One of the elements was 28 millimeters in diameter, and an exaggerated profile of the asphericity is shown in red. And then we predicted MTF, we predicted all kinds of things, and eventually the system worked very well. Unfortunately, the project was canceled. And if you look at some of these predictions here, and then I'm going to skip these, but I am going to settle into one of the, you can see almost an exact duplication of what we were predicting based on measurements of the surface. Let's see what else we can do here. Okay. Well, that was a pretty big study, let me tell you. Tolerances don't lie. If a quarter wave represents, you're standing on the edge of the Grand Canyon and someone gives you a little push, they're going to introduce a quarter wave figuratively to your position. If they push you much harder, you're going to fall in and you'll be up to half wave and a wave, and then you'll fall down, you'll have lots of aberration, and the performance will get bad very, very fast. So you've got a little bit of margin built into most good designs, but not a lot. This is from a study Alistair did on 70 separate lens elements, comparing measured values with what the specification was. And the spec was right along here at 100% of the tolerance level. And then what we found is that there was something like 82% were within their thickness specification. That says 18% were out of spec. Now that's a good optical shop, good reputation, and so forth. So one has to watch these suppliers and vendors like a hawk. This is another cell phone application. Diffractive optics, should I keep going, or where am I?
You got about 2 minutes.
2 minutes, okay. Could you tell me when I have 1 minute? Okay. Diffraction gratings are basically rulings on a piece of substrate material, and we use diffraction. Let's see, where's my favorite slide? There it is. An ordinary lens, the blue focuses here, the green and the red. If this were a diffraction grating, the red, because the wavelength is longer, focuses here. That's out of the grating equation. Then the green and then the blue. So basically, you can have with one material, with a diffractive and a spherical surface, you can bring the red and blue to a common focus. And that will be present in future designs. That's an eyepiece we have a patent on. I'm not going to bore you with that. This is just fabrication types of pictures. As I said, if you can, I'd love to tell you about it. If anybody's interested, this is called magnetorheological finishing, one of the more significant advances in manufacturing, probably in this century or the last century. Stray light suppression. This is a true story. I won't tell you the whole story, but I will say that it's a friend of mine who had a machine vision company, and basically he made a new camera, and he got stray reflections from the inside walls, which were anodized, machined and anodized. And ultimately, what we did is we put low reflectance paper, like flock, they call it, inside of this. And then in addition, we illuminated only what he was interested in, not Hull's half acre down here, which was bare aluminum. And his performance got not only good, but it got better than it ever was. More stray light suppression for telescopes. This is the Cassini mission. Am I up to my minute yet? Off-the-shelf optics, I'm not going to talk about because of time. I think that's actually the last one, believe it or not. Now, I'm going to simply say here that today's talk is the ever-increasing performance of digital imaging, specifically cameras, and the requirements will continue to improve of the optics. It has to. Smaller pixels, smaller image blurs, lower F numbers, more compact, higher MTF and contrast. New lens technologies, compact zooms, new lens materials like the Casio. More use of precision A-spheres, diffractive and spherical surfaces. Improved stray light control and lower cost optics will all be required, and that's rather complex. So fasten your seatbelt, hold on to the safety bar. It's going to be a very fantastic ride into the future of imaging optics. Thank you very much for a great talk.